Hello everyone, it's January the 10th. I just watched, ask me like what type of videos I like to watch these days. I went through different stages, and then these days I just go back to the old videos I watched all the time. Clarence Kennedy. I just watch Clarence video, it gets you into a very different mindset. You're in a very different place. I have a bunch of those old videos I really like, really like. You know, the power, the strength, and the beauty in all of those. Man. Something that I know I will never be able to achieve in my lifetime. But it's good to look and to dream. Alright, what the hell is this one? Minimum time to collect all apples in a tree. Okay, I see what you did there. This is a tree, and then we have apples. Give an undirected tree consisting of n vertices, number from 0 to n minus 1, which has some apples in their vertices. You spend 1 second to walk over one edge. Return the minimum time in seconds you have to spend to collect all apples in the tree, starting at vertex 0 and coming back to this vertex. The edges of the undirected tree are given in the array, in that there exists an array. Okay. Additionally, there is a Boolean value has apple, where this indicates this one has apple. Otherwise, it does not have apple. So for the first one, we're gonna go collect, collect. So it's gonna be a one traversal, right? Huh. What does it matter? We go this way. 1, 2, 3, 4, 5, 6, 7, 8. It does not matter, right? 1, 2, 3, 4, 5, 6. 1, 2, 3. 1. We don't do this because it's waste. So 1, 2, 3, 4, 5, 6. Huh? I don't really think it matters. You just traverse the tree to hit all these things. So basically, it's the trips you need to get to this, right? To get to this and to get to this, and then double it, because that's 1, 2, 3, 4. 1, 2, 3. All right, so just all the paths needed, which basically means so we're gonna traverse the tree to hit all of them. And so when we hit, we get the number of paths used, and then just double it by 2. Make it look like it's something else. Oh my god, look at this thing. Yeah, we still have the problem from yesterday we haven't solved. But that's okay. What the hell? All right, so what do? We are going to be... I'll just traverse the entire thing. We can even do it... Nah, BFS I think will be easier. Not DTFS. Paths. Level. Right? Not really level. Number of edges. I don't have to return anything. If node. Oh, it's not node, index. Oh, if it's index. If index, if has apple, index. num plus equal 1. Right, if this, then self.rest equals 0. Then self.rest plus equal num. Alright, and then all the edges. Oh my god, we have to deal with the edges. Oh, maybe not. Oh. It's a tree, so I just need a parent. Ah. All right, and then DFS 0. Alright, this is 0, so we're going here will be 1, here will be 2. What the hell? Oh. That. Sorry. That's not what I had expected. Oh, we added a 0. That's fine. We'll just do it there. Ew. Let's see. How is it 10? Oh, it is 10. 1, 1, 2, 1, 2, 2, 2, 1. Oh, hold on. Oh, is the number of... Oh, shoot. Now, that's not right. That's not right. Oh. Then we have to do BFS. Oh, we have to do BFS. This doesn't work. right? We probably have to have visited in this case. What? Oh yeah, we added twice again. Darn. All right, so how do I know we're on the same level? We need to have something has how do I do this? We do like this. Num apple. If we have, then rest plus equal to level plus num apple. That's also not right. That I don't understand. I said on this level, right? On this level, when you reach this level, too much. Because the level is this, so it should be level -1. That's the way to go. Yeah, all the apples, right? All apples on the same level needs uses the same I'll have to just count the number of paths, right? Count the number of paths. And it gotta be an easier way to do this. I mean, let's submit this first. It should be right, but it feels so complicated. And it's not right. What the hell? That's still not number of paths? Oh man. 6. What the hell? 0, 1, 1, 2, 0, 3. 1, 2, 3, 4, 5, 6. Yeah, only have 3. Why do I have... The hell is this? No. I just want to know the total number of paths. That's all I need to know. Total number of paths. How do you calculate total number of paths? All right, change your mindset. Change your mindset. I want to know the total number of paths in this, right? So I go to this, and I need to know the total number of paths is here, right? Total number of paths inside this subtree. Once we know that, we just need to add this one. Once we know that, just need to add this one. Change, change, change. This is not working. Okay, and then we're gonna return integer. Okay. Now what we want to do is I want to go to my children to know the total number of paths in this. Okay, so okay, you can say DFS. Okay, so there's a total number of paths on this side, right? And we need to also return if it's in there. So that should be a tuple of int and a Boolean value. Okay, so num path and then has apple. Okay, we say if has apple, then res plus equal to number of paths on this one, right? Total number of paths on this one. And then plus 1 plus my path, right? If it does not have apple, okay, in this subtree, if it does not have apple, then it's nothing. So I might just do plus int has apple. Or might just, let's do this int. Nah, I don't like it. So res apple. As long as one of them has apple, so this will be false. Next has apple. Next num paths. Yeah, num paths. And then has apple. Next has apple. Not num has apples next. Alright, so go through all them, we just return num paths and has apple. And then we call DFS 0 minus 1 has apple index. And return 0 times 2. This is frustrating, man. What the hell? Just 3. How? All right. 1. Num path is 2. And then has apples false. How is it false? And where is 4 and 5? That's 4 and 5. 4 and 5 is true and true. So return. There should be 1 and 1. So we go 1. That's 2. Has apple was false. But oh, not equal to. Jesus. Oh. I cannot. This is giving me a hard time. Count the number of paths in all the subtrees. Number of edges. Unique edges in all the paths that lead to an apple. This. Come on. How should I say? Sometimes it's just you thought it's gonna be one solution, right? But it's not. This is very frustrating. Waste a lot of time. What's the difference? Child time. Oh. That is true. That is true. But I like the way I do it. And yeah, that's it. Yeah, it's pretty easy. But, you know, sometimes this happens. All right, split message. We have error cases. Is this one's error? Yeah, this one's error. So I think what I said is we are going to find the upper bound. Okay? And then we're going to do binary search in 1 to 10, 1 to 9, 10 to 99, because they are all the same. Okay, we can avoid or these, you know, things. You know what I mean? So we're gonna say we got low and high, right? And then we say if it's this, high equals this, until else I'll break. Okay. Now we have the thing. Now we're gonna do another function called binary search. That's a binary search. I call it minimum partitions. Okay, minimum partitions. Then we have the low and high. Okay, we have low and high. And then what? What do we need? We need n, just the length of the message. That should be good. And then this will return an integer, right? So what we can do is just put everything here. Okay. And then it won't be that complicated. Low and high is just with one single degree. So in fact, I'm gonna cancel this. This one might be using here. So it's a single degree, and we have low and high. I just want to see, right? We want to see, we binary search, and see, right? We just want to see if it's possible, right? If it's possible. So we're gonna say, because the mid have mid number, so this is fine. We can do this, right? This is a mid minus 1, length of this. Oh, it actually doesn't matter. We can just do this, which is fine because they're all of the same. So we say low and high must have same number of digits. Okay, so mid the same number of digits, so we get a k, right? And then start is gonna be this, and is gonna be this. That's correct, right? That's start, and that's end. So in this, well, in fact, the start is destined to be low, right? The start is destined to be low, brother. No, low and high is the numbers is not. Hold on, let me think again. Yeah. Low is the smallest, high is the biggest, so it's always gonna go low, right? Until it's impossible. Then we're gonna go high. And then no, that's the number of partitions. That's the number of partitions. That's number of partitions. Well, what is this that we're talking about? Number of partitions. Hey, hold on. Number of partitions. Number of partitions, right? We can say number of partitions in this. So okay, this is the number of partitions. So we say I have 10 or 20 partitions, and it's guaranteed when I start from a double digit. When I start from a double digit, that's the whole purpose. When I start from a double digit, right? So all we need is just the end. We're just going to be n mid minus 1. So we just need to calculate from low to mid minus 1, right? Because it's 2 digits. It's always going to be from low to there. So we're gonna mid. We just want to see all of this. Can we fit into it? Right? Can we fit into it? Shouldn't we be saying okay, so number of parts, that's the number of parts. And then we say, let's put everything in one digit. Okay? And then if one digit doesn't work, then we say, okay, then the remaining will be put into 2 digits. And we try to fill 2 digits. See how far we can go. Yeah, shouldn't that be the case? No, that's not the case. Because if we say we want to fit in 1 digit, then the end will be 1. Right? And if it doesn't work, then we know we have to have 2 digits. Yeah? Yeah? So that is the way to go. What you're saying is we're going to try to fit in 1 digit. Right? And we say k equals 1. 1 digit. And we say while true. Okay? So 1 digit, we can compute the maximum length we can fit. Okay, the maximum length we can fit with k equals 1 is going to be max fit. Okay? Now we're talking about k equals 1. The maximum we can fit k equals 1 is going to be the total number, so 10 to the k minus 1. That's the total number. That's not true. That is not true. It should be, this is the last one. This is k minus 1. This is the first one, right? So this minus this. So 10 minus 1, 9. This is the number of partition. Max partition is going to be this. Right? We have the max partition. And each one is going to carry, right? Each one is going to carry so it's going to be limit, right? Limit minus k minus, because k is 1 digit value, minus k, minus 2 times k, minus 3. That's the amount we can fit in every single one. So max fit plus equal to this, right? That's the max fit. And we say if max fit, right, is larger or equal to n, that would break. Or we can say max fit smaller than n, then we keep going, right? If it's larger, right, so, and then, actually can set k equal to 0, and then k plus equal 1, then we do this, and then max fit smaller than n, with n, k plus equal 1, so k equals 2, right? So it'll be 100 minus 10 is 90. So 99 minus, yeah, it's 90. So of all of them, we can do, so at the top, what's the max fit? Oh, shoot. That's not right. Because we got 2, the max fit of the previous one will decrease. Ah, you bloody hell. So, dude, man. Oh, Lord. Ah, Lord. And we have other limits. Yeah, given a current k, right? Given a current k, I know I need to occupy 2k, right? This is what I need to occupy. This is what I need to occupy, and if this must be smaller, equal to limit. Because actually, if it's equal to limit, then we can't do anything. Right? Then what's the point? So it has to be smaller. And then max fit. Limit, this is the new we can add, but we need to minus. Minus all of the previous. Because we add one, right? So it should be this is what we can add. Is this times max partitions. Right, this times max partitions for the current number of digits. For each one we can get one of these. You know what? I don't feel comfortable. If this and if max is larger or equal to n, break. Okay, so we find the max part, and now we have n, and then we'll calculate. And this is the require if this is smaller than the limit, then which means this has some to do, otherwise we'll break. Right? And then this has to minus, because every time we do this we need to minus. What do we minus? So now we have, so all the previous, right? So it's 10 to the k, right? So for example, if we do 2 digits, then all the 1 digit need to move 1, right? So this is, so k is 2. All right, k is 2. So the 1 digit need to be k minus 1. Right? That will be 10 minus 1. Yeah, every time we go to the higher number of digits, so we're going to go to the lower number of digits. We have all of them. Everyone need to remove one more because it's one more digit. So that's the max fit. This is the current maximum number of fit. And then if this, so blah, 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 so it'll come out, right? Then we say if come out max fit is larger equal to n, then we say it's good. Then we will do this. Or we can say if max fit is smaller than n, then we just return this. Impossible case. Otherwise, we try to figure out number of parts. Number of parts. I don't know. I just know k. Right? I just know k. So what do I do? So when I get out, I have k. K is the, I know the largest, right? So I shall say number of parts. I don't know the number of parts. I just know to this I can fill, but I don't know where. So we need to fill out, right? To take this will be k. It's in start. This should be to 9, right? From start to end. Shall be the minimum of this and n. Put I to this. Num parts. Holy crap. I don't know what is num parts. I'm gonna replace English letter. So we don't know. So we'll replace with this. Okay. And then this will do this. No, that's not true. What we need to do is keep going until we hit. So while I is smaller than no. So end initial is to 9. No. So in this we know it's gonna be k number of digits, right? K number of digits. So we know how many we need to go. Right, we know how many we need to go. I have k number of digits, so the last one we do know. right? The last one we do know. This is the number of partitions. And as I go, J just keep incrementing, right? J keep incrementing and I keep going until a moment I cannot go. So I don't need end, I just need to start. Times st. That's gonna be minimum and okay, J and this plus this and J, and then here if J is larger or equal to n, no I, that will break. Right? Then we will break. When we break out, we check again. If I is larger or equal to n, then we'll break, which means here should be I smaller than n. St times equal to 10. Okay. Then we'll return for r in res, r dot replace star with j. Oh, it's in this thing. All right. Let's see if this one is right. This one is correct for this one. It's correct for everything. Okay. Try all the edge cases. Let's try these. Okay. That is correct. So no binary search. First, we try one digit number of partitions. If that is not sufficient, try 2-digit, then 3-digit, etc. until we find the number of digits in the total number of partitions that can fit the given message. Then we perform the partition, right? One per digit partition at a time. Right, that means we do one total partition to 9 total partition, then 10 total partition. I should say 1 total. And 10 total to 99 total, then 100 total, and 999 total, etc. There is a trick. Since we don't know the number of digits in the total number of partitions, we cannot fill that number up initially during the construction of the result. We simply put a star there. Once we have completed the partitions, we can replace the star with the total partitions. Which is at ON. Yeah, I think it's ON. Because here, this is actually not. This is a log n, something like that. But this is ON. So we have to go through this and then go through this. Yeah, this we have to go through every single one, unfortunately. So I'll call it ON. I mean, the runtime was good. Oh my god. Oh my god. Current plus length plus this times k. What's current? Total plus, oh, the total needed. 3 plus this. Oh my god, this is good. Same idea, but well, better. All right, and now do this. This is to take. What? What the hell is I? I is 0. Oh, k is 1 at a time. I thought k is... Oh. The number of partitions. K is the number of partitions. They just do it one at a time, one at a time, one at a time. Ah, so we can do it one at a time. I see. And then, yeah, we just, for each partition, we'll get... So yeah, now I know the total partitions. Ah, this will be easy. I know the total partitions. This I do not know the total partitions. I actually make it faster in here, but it's overall it's the same. Anyway, that's all right. Okay, so yeah, this one is not difficult. Binary search is redundant. Yeah, I was stuck to binary search. So the benefit of this is I don't have to search. I make it a little bit faster because in the first part, it's a very fast search to know the number of digits. And then in here, it's basically, it's the same thing. It's a little bit more thinking in this part. I know we don't know the last one. But yeah, then you have to do this, right? Which is exactly the same of this. So yeah, overall it's the same. Overall it's the same. You just need to search for every partition. For every partition. You know what? I want to do this again tomorrow. To search for num partition first, and then yeah, I want to do it again. All right, I'll see you guys tomorrow for this one again. Adios.